Hey, welcome back to your favorite pre-calc class, trigonometry. We're going to take a look now at, finish off this section into area of a sector. So the area of a sector, the formula is, if you have a central angle theta here in radians with our r radius, this area, right, how much area is given by this formula. Now let me tell you where that comes from, okay? Let's set up a ratio. Let's set up a proportion here, two ratios together. Let's say we have that area, and we're going to compare it to a full revolution. So the area of an entire circle. You know, if we go all the way around, then we have the area of the entire circle. Let me call this theta 1 and area 1. Okay. So theta this is a proportion here. Theta, this sector over here, right, is to the full circle, theta 1. That ratio is equivalent to the area, again, of the small sector over here to area 1, the area of the entire circle, which we know the area of the entire circle, go up here, we know this area to be pi r squared, and we know if we do a full revolution around, right, that theta 1, that's 2 pi, a full revolution in radians here. So we have theta is to 2 pi, full revolution, as the area of the small sector is to the area of the entire circle, pi r squared. So then we just cross multiply. So we got area times 2 pi, so we got area times this number equals theta times pi r squared. I'm going to solve for the area of the sector, so divide by 2 pi, so my pi's cancel. So what we have is a half, right? So I have a 1 here, and there's my half. 1/2, I got the r squared right there, and then I got the theta. So that's the area of a sector. That's where that comes from. So let's go ahead and do it here. Find the area sector of a circle of radius 3 meters formed by an angle of 45 degrees. So it's only rotated 45 degrees. Now we can't do 45 degrees. We've got to have that in radians. So number one, we're going to convert that 45 degrees times pi over 180 degrees. So we get pi force radians. That's the first thing. We've got to make sure we're in radians. Now we're trying to find the area of this sector, right? So the area is 1/2 r squared theta, and it looks like the radius here is 3 meters that they gave us. So we have 1/2, we got 3 meters, which is squared, times our theta, which is pi force. So this area ends up being 1/2, we got 3 squared, so 9 square meters. And we got the force, we got 9 force, and we got the pi as well, so we got, we got the 9/18 on that. So that ends up being, or I'm sorry, 9/8 pi. And this is square meters. Let me punch that in. And we got 3.534291735 square meters. And we can 3 point. All right, so that's the area of that sector in square meters, right? All right, let's get into linear speed and angular speed now. So linear speed, let's suppose that an object is moving on a circle of radius r at a constant speed, right? If s is the distance traveled, right, the arc length that it covers, in time t, then the linear speed is, so this is the distance traveled, the arc length. So it's distance traveled, again, that's the arc length, as it compared over how much time? Time t. So like the example we're going to look at, like let's say you have a rope and you're spinning a rock, right? Like you're spinning a rock in your hand, right? The rock's on the end of the rope and it's spinning around, and let's say it's spinning around at, I don't know, it covers like 220 feet in 1 minute, right? It covered 220 feet in just 1 minute. That's your linear speed, okay? So that's what that means. So v equals s over t. Linear speed is your distance traveled over your time t. Angular speed, on the other hand, is the angle that's swept out over the elapsed time. Okay, so like a lot of the time, you might think of with angular speed like turning rate of an engine. So if an engine's idling at 900, and by the way, this is omega. This is lowercase omega, by the way. So theta, how much is swept out for time t? So like, let's say you have like 900 RPM, revolutions per minute. Okay, that right now is in, this is an angular speed. Now the problem is this angle theta, this has got to be in radians, not in revolutions. Right now we're in revolutions. And I'm like, well, I know for every one full revolution is 2 pi, right? So there's 2 pi radians for every one revolution. And now, so I have 1800 pi. That's how much is being swept out every minute, right? That's how much it's rotating, 1800 pi, however many times per minute in a minute, right? So really quick idling speed for that engine, but that's its angular speed. Okay, so we've got linear speed, v equals s over t, and then we've got this angular speed. Now, how do they connect? Well, if you think about it, this is our arc length, right? So s equals r times theta. And notice, see the theta over t? What's theta over t? That's our omega. So if I replace this with omega, that's how they're related. The linear speed is equivalent to the radius of the circle times its angular speed, omega. Okay. All right, so here's your example. Child spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. Okay, so it's giving you that angular speed. Let's go ahead and find the linear speed of the rock when it's released. So number one, what are we given? We're given 180 revolutions per 1 minute. Now this needs to be in radians, right? Remember, omega's got to be in radians. We know there's 2 pi radians for every 1 revolution. So we have 360 pi radians per minute. Okay, here's our omega. So number two, now that we have omega, I'm going to use that, instead of s over t, angular speed is s over t, I am going to use that last one there, v equals r times the angular speed, because I have my angular speed. So let me go over here. My rope is 2 feet, right? See our radius there's 2 feet. So r 2 feet times our omega, 360 pi per minute. So it looks like we have 720 pi feet per minute. Okay, so you punch that in, 720 times pi. Let's see, we had 2261.946711 feet per minute. Okay, now let's make a little more sense of that. Let's put that angular speed in miles per hour. Okay, so I've got 2261.946711 feet per minute. Now I know there's, for every mile, so I'm trying to get to miles per hour, there's 5,280 feet. 5,280 feet. Notice my feet cancel. Now I'm in miles per minute. I want miles per hour, right? So I know there's, let me multiply, let me get rid of my minutes. There's 60 minutes for every 1 hour. Now my minutes are gone. So I have 2261.946711 times the 1 times the 60 divided by, on the bottom I just have 1 times the 5,280 times 1. So I just divide the whole thing by 5,280 on the bottom. And I get approximately, let's see here, 25.704 miles per hour, given that initial angular speed. Now I have my linear speed and I put it in miles per hour. Well, thank you so much for listening. That's the end of this section. We'll see you guys next time.